One more. Okay, Assalamualaikum and good morning. Okay, so today we proceed to discuss the last chapter on control rectifier. So before we proceed to go further to discuss on three-phase rectifiers, so let's take a look the exercise that we have discussed last week. Okay, ready? Okay, so this is the control rectifier. So we apply thyristor for thyristors. So where the thyristors on in pairs. So this case, for example, so when we inject the current pulse, we apply the same current pulse to the gate terminal of S1 and S2, the green color here. So then these two SCR will connect together at the same time. So this will turn on for the first half of the cycle once the current pulse is injected into the gate terminal. Okay, then for the next half cycle, means the second half cycle. So when we apply the current pulse, the blue color here, to be injected to the gate terminal of S3 and S4. So these two thyristors or SCR will turn on. Okay, so here, so as a result, it will produce the output voltage, which is the waveform with the orange color here. Okay. So you can notice because of the inductive load here, so you have to take note or take into account that the nature or the behavior of the inductor current, where the current cannot be immediately changed, same as the voltage. So due to the storage energy elements, so the current need some time for it to charge or discharge. So that's why you can have continuous current here, the blue color. So this current, the continuous current, allow the SCR to be conducted. Even the angle here is even the angle beyond the pipe. So mean it has the extension angle for the SCR to conduct. Okay, so we have discussed how to derive the output voltage here. So actually the output voltage, you can use this definition, which you can obtain the output voltage, which is the area divided by time. The area divided by period. So the period, this case is pi, it's not 2 pi. And because this rectifier is full wave rectifier. Okay, it's not the half wave. So mean full wave, the period will be pi. It's not 2 pi. Okay. Okay, so this is how to derive. Then we must know how to calculate the output current here using the Kirchhoff voltage law to calculate the power absorbed by the resistor and the DC voltage here. So we have to take note the RMS of the output current is same as the average component of the output current. Okay, then this exercise. Okay, based on the information given here, the source, which is 240 volt in RMS at 60 Hz, the DC voltage here is 100 volt, R is 5 ohm. So you need to calculate the alpha, the firing angle, so that the power absorbed by the DC voltage here is 1 kilo. Okay, then you need to determine the value of L. So you have to design the value of L so that it can limit the peak-to-peak load current to 2 ampere. Okay, so this is the process how to answer the question. You calculate the DC power, the power absorbed by the DC voltage. Then from here, you can calculate the output current. So you apply the Kirchhoff voltage law to calculate the VO and the output voltage. So then from the output voltage, you apply the equation here. Okay, this equation. So then you rearrange to solve for alpha, the required firing angle. So then you get the angle is 46 degrees. So you can provide the answer in degrees or in radian. Okay, then from here, next part B, you need to design the inductor in order to limit the current ripple. So you need, in order to simplify the analysis, so we need to apply the assumption where the variation of load current is mainly affected or influenced by the first AC term. First AC term for this case is I2. For the single phase control rectifier, I2. So then from here, before you calculate or obtain the impedance, the Z2, so you need to estimate the V2 first. So the V2 you can estimate it by from the graph below. Okay, so we have calculated the angle, the firing angle 46 degrees. So then from here you can obtain the ratio between V2 and VM is 0. I don't know what is value, 0.68. Okay. So then from here you can calculate V2. Then you can calculate the impedance. After you get the V2, you estimate the V2, you can calculate the impedance, the required load impedance, which is 230. So you need to apply another assumption in order to simplify the analysis. So where the effect of resistor you can neglect because the value of R is too small, 5 ohm. When you compare with the total impedance, which is 230, so the R value is too small. So then we can neglect the resistor. So then from here you can calculate the required inductor. Clear? Simple. Okay, so before we proceed to discuss the next section, 4.4, so where the converter can operate as inverter. Okay, just now, for the exercise 2, we discussed the rectifier or the converter operate as a rectifier. So that's why you get the output voltage is positive. So the next session, we will discuss how the converter can operate as an inverter. Okay, before we proceed to discuss this section, the next section, so let me demonstrate the simulation in order to verify the calculation in exercise 2. Exercise 2. So where the exercise 2 ni, okay, so this exercise 2, so we try to model the simulation. So where the source is 240 volts, okay, clear? 60 Hz DC voltage is 100 volt. Okay, so this the source voltage here. So because this parameter box require information in peak amplitude, so mean the amplitude. So it means you have to multiply the RMS voltage with square root of 2, right? Set 2, right? In order to get the VM. Okay, clear? Frequency is 60 Hz based on the question here, 60 Hz. Nampak 60 Hz. So this is the single phase control rectifier. So DC voltage is what? 100 volt. Here, DC voltage 100 volt. Okay. Then your R value, here your R we set is 5 ohm. From the equation is 5 ohm. And the design of inductor is 0.305. 0.305. So then here we need to set Here it must be R5 ohm and 0.305 Henry. Unit is Henry. Okay, now we can try to simulate and observe the result. Right, mana simulation? Where is the simulation? There. Okay, so the top graph plot the waveform of the source voltage. The yellow color is the source voltage, which is a function of the sine, sine function. The yellow color. The blue is the output voltage. Okay. So the second graph here, the yellow color is the output current. The blue color is the source current, IS, source current. The yellow is the IO, output current. So the bottom graph here is the current pulse for thyristor 1, 2 and thyristor 3, 4. Thyristor 1 and 2, the yellow color. Current pulse with the yellow color. Current pulse with the blue color is the current pulse for T3 and T4. As here, T3 and T4. Okay, so I forgot to mention the current pulse is generated from this unit, the firing angle control unit here. Okay. Actually, you can design this block if you understand how to the way the current pulse produced. So actually, you can design the current pulse. This block, sorry, you can design the current pulse firing angle control unit. So you need to provide the information of the angle and the source. So maybe I can show you what is inside of this subsystem block. So this is the way lah. So maybe you need to think lah the algorithm how to generate the current pulse. So here for T1 and T2, and the bottom here is for T3 and T4. So I no need to discuss this one. Explain if you are interested to know how to design. So you can come to see me at my lab. Okay, so this current pulse T1 and T2 in pairs here will be T3 and T4 will be injected to their respective gate terminal of the thyristor. T1 here, T2 here, T3 and T4. Okay, so then we verify the result. So here is the current pulse. Before that, maybe we look at the display here. Okay, so in order to get the DC component, so you need to put the min block here. Okay. Then the display will show the output voltage component, the DC voltage component 150. Okay, same as the calculation. Betul tak? So the DC is 150 volt. Okay, we will verify the calculation value. Angle is 46. So that's why here I put the angle is 46 degrees. And the output current here, 10 ampere, almost same. And the simulation result, 10.01. IO here is 10 ampere from the calculation. Okay. So then we also can prove that the IO average, the DC component of the output current, same as the RMS output current. Okay. Almost similar the result. Okay, then because in part B you need to limit the current, right? You have to limit the currents such that the current variation ripple will be what? 2 ampere here. And you have designed the inductor. So then where the current variation, the peak to peak current variation must be not more than 2 ampere. So then from here, from the result, this is the output current, the yellow color. So maybe we can magnify the result. So then from here you can see the current ripple, which is the difference between the maximum and the minimum output current variation will be almost 2 ampere. Clear? 11 minus 9, almost 2. Okay. So this result, maybe the other error, slightly greater than the calculation. But the error is too small, less than 5%. So the result can be acceptable. Okay, clear? So this is how you verify the calculation through the simulation result. Okay, any question before we proceed to the next section 4.4 regarding the ni lah simulation model. Okay, so please take note for the converter to operate as rectifying mode. So your DC voltage, so you must connect to the in right polarity. So mean the plus must be at the top, minus will be at the bottom. Okay. So this is to operate the converter as a rectifying or rectifier. Okay, for the next section, 4.4. Okay, so you same circuit, but now please take look at the polarity of the DC voltage, where the positive sign at the bottom side and minus sign at the top side. So you need to change the polarity of the battery. Okay, so for the conversion of the transfer power from AC to DC side. So this is the AC side, because you have the AC source, single phase AC source, and at the load is the DC. And so this is the DC side, here will be AC. To transfer the power from AC to DC, so you need to operate the converter as a rectifier. So mean here, we can say that for transfer from AC to DC, so the converter operates as a rectifier. Or maybe I can write as a rectifier operation. Okay, right. Fill in the blank. Rectifier operation. Otherwise, when the power transfer from the DC to AC source, so in this case, the converter, so maybe I can define this bridge as a converter in general, because we can operate this converter as a rectifier or inverter. So this is the bridge or rectifier, converter or bridge converter, sorry. So mean to transfer from DC to AC, so mean the converter will operate as inverter. So mean I write inverter operation. Okay. So the application for rectifier operation, for example, battery charger. Well, and because you transmit the power from the AC to charge the battery. Okay, you charge the battery. So mean the DC voltage, the polarity must be opposite. The plus at the bottom, minus at the, the plus at the top, minus at the bottom. Okay? So when you operate the converter as a rectifier to charge the battery, for the application of the battery charger. Otherwise, for inverter operations, so this will be the PV, grid system, or maybe I can write as a solar cells or PV system. Or maybe you can represent the DC voltage as a DC generator, because you generate the electricity to transfer to the grid, to be injected to the grid, AC source. So mean your power in opposite direction from the DC to AC, the red color here. Yeah. Okay, so the converter can operate as an inverter if power to flow from the load to the AC source, the red color here. So mean you transfer the power from the DC, from the battery, from the solar cell or DC generator to AC or to the grid, utility grid. Utility grid, you try you inject or feed the electric energy to grid. Okay, to operate the converter as an inverter, so the power must be supplied by the DC source, PDC. So where your PDC is the power supplied by the DC source is equal to what? Multiplication between the DC voltage and IO. So remember, your IO is the output current. Okay, then the power must be absorbed by the bridge and transferred to the AC system. So this is the AC system. So the bridge absorbs the power. So we can define as PAC or P sub AC, which is, you can write the equation as minus PO multiplied by IO. So don't forget to put the minus sign here. Okay, minus sign. Right? Okay. Okay, then power absorbed by the resistor. So where the power absorbed is PR, you can write the equation as the RMS squared multiplied by R. Okay, so we can equate the RMS current as IO because RMS and the output current are same. We consider same value. So where RMS can be set as IO and the output current. So remember this is DC, DC component of the output current. You multiply by R. So mean for the inverter operation, the PDC, the power delivered by the DC source or the solar cell DC generator is equal to the summation of the power absorbed by the resistor and power absorbed by the bridge. This equation. PDC must be larger than PR and PAC. And because you transfer the power from the DC source to the AC. So mean PDC always larger than power absorbed by the resistor or power absorbed by bridge. Yeah. Because you transfer the power from the DC source. For the rectifier operation, PAC will be large, always larger than PDC and PR. And for a rectifier operation, because you transmit the power from the AC to DC. Okay, so one thing you need to take into account that for the inverter operation, the current direction must be in direction, same direction with the rectifier operation. Mean your current maintain the direction, same as when the converter operates as a rectifier. Yeah, because of what? Because due to the polarity of the thyristor. So remember your current, the thyristor allow the current to flow from anode to cathode. Here will be anode, cathode. So same goes to here, anode, cathode. So mean the current direction is same as when the converter operates as a rectifier or rectifying mode. Yeah. So IO always positive. You cannot change the direction of the output current due to the polarity of the thyristor. But VO you can change the sign. So remember for rectifying mode, for the case of the converter to operate as rectifier, your output voltage will be positive. VO will be positive. But for the converter to operate for the inverting mode, inverter operation, the VO must be negative. And VO must be negative. But the output current, the output current direction are same for both operations, rectifier and inverter operation. Clear? Boleh dapat tak? Okay, bagus. So then, okay, next page. Okay, so this is the inverter operation. So before we derive, before we look at the output voltage equation, so you need to know how the production of the output voltage. So means to sketch the output voltage. So from the output voltage waveform, then you can know how to get the output voltage equation. Okay, so remember for the inverter operation, the polarity of the DC source must be like this, plus at the bottom, minus at the top. So the current direction still maintained as the rectifying mode. Okay, you inject the current pulse, same for S1 and S2, or same goes for the S3 and S4, the orange color. So we know that the DC source, sorry, the power delivered by the DC source is the summation between PR and PAC. So this is the way you write, you substitute the equation that we have shown previous page. So then you can write this equation. Okay, now, so this is the profile of the output voltage. So the output voltage versus angle, the firing angle, alpha. Okay, where the output voltage, okay, so the output voltage here, so maybe I write different color, PO. So actually we have discussed last week, VO is 2Vm divided by pi, you multiply by cos alpha. You right? Ni. Which part? Maybe here. Ni. 2Vm per pi cos alpha. Based on this wave shape of the output voltage, so you can calculate the output voltage, which is actually is the area divided by period. So then you apply the trigonal identity, blah, blah, blah. Then finally you get this equation. Okay. And then 2Vm per pi cos alpha. To mean here, this equation. So from here, so actually you can get two region. First, your output voltage can be positive. Otherwise, your output voltage can be negative value. Okay. So the positive output voltage can be obtained if you design or you produce, you design the delay angle from 0 to 90 degrees. Is it right? So this is alpha, the firing angle, 90 degrees. You can try to verify using calculator. You set cos from 0 to 90. So you get positive value. Okay. And you can get the negative output voltage if you set the alpha between what? 90 degrees to 180 degrees. Okay. Is it right? Okay, let's say you set your alpha is 0 here. 0 angle here, 0 degrees. So what is the output voltage? Based on this equation, you set alpha is 0. So mean you get cos 0 will be 1. And cos 0, 1. So then you get the maximum output voltage, which is this point, right? The blue color ni. So this is the maximum. So where the value of the output is 2Vm divided by pi, where the value is positive. Then you can change, you try to set the alpha from 0 to 90. So actually you can get this profile of the output voltage, right? Ni. Sengaja saya buat dash line ni. Okay. So when you set your angle is 90, cos 90, then the cos term will be 0. So then your output voltage will be 0 here, this point. Okay, so mean from during this process, you change from your alpha from 0 to 90, the converter operates as a rectifying mode. Okay, rectifying mode because your output voltage is positive. Positive value here, positive value. But then you set your alpha from 90 to 180, so then you can get this profile of the output. So where the output voltage is negative until to this point. Yeah. So let's say you set your alpha is 180 degrees. So mean cos term will be minus 1, right? So then you get the minimum output voltage. So where the minimum output voltage is minus 2Vm divided by pi. Okay. So actually this profile, you can sketch this profile based on this equation, VO sorry, 2 Vm divided by pi cos alpha. Okay, clear? So mean it's possible the output voltage can have negative value. So mean indicating that the converter operate as inverter. Yeah, inverter. When we said the converter operate as inverter, so mean the power transfer from DC to AC. Because now your VO is negative. Your VO is negative. So mean the power flow change the direction from the DC to AC. Clear? Make sure you understand this topic. You may have two questions on rectifier, control rectifier in your final exam. Two questions, I think. Two questions. Okay, any questions so far? Okay, so we proceed to the next page. Okay, so your output can have positive and negative value according to the angle, the delay angle. Okay, so so you have this profile, kan? The output voltage profile. So maybe we need to sketch first. So you have positive when your alpha change from 0 to 90. At 90 get 0. Then you can have negative output voltage when the alpha change from 90 to 180 degrees. Okay, so here, how to sketch the output voltage? So let's say for rectifier operation, where you need to set the angle. So the angle must be in between 0 to 90 degrees, right? For inverter, 90 degrees to 180 degrees. So let's say, for example, we said alpha is what? Between this range, 0 to 90, maybe we said 45 degrees. So how to sketch the output voltage waveform? Okay, so here is 0, right? 0. Then this point will be 90 degrees, right? 90 degrees. Here will be, sorry, 90 lah. 180. Here will be 180. So 90 will be here, right? This point, 90. Okay, for 45, so mean you need to inject the current pulse at this point. So this is 90. Here will be 45. So means the current pulse here you inject. Okay, sorry. Please catch. So mean you have to inject the current pulse to this point. So here, what color? The blue color for S1 and S2. Which one is the blue here? Yeah. So you inject the current pulse here. So this is for S1 and S2. So once you inject the current pulse here, so mean your output voltage will be same as the source voltage. So mean here, source. Okay. So your source will same as Vs, right? Okay. So mean this case, your thyristor 1 and 2 will be conducted. But it's still maintained to be conducted due to the current. And the inductor current, the nature of inductor current. So remember, we must assume the current is continuous. So mean the S1 and thyristor 1 and thyristor 2 will be conducted. when the angle beyond the pi. So mean it will continue to conduct. So that's why in this case your output voltage will be the same as Vs. Okay. Clear? Vs. So then when you inject the current pulse for S3 and S4, so mean here at which point? Maybe I need to erase this one first. Orange color. Ni asal pen color lain. Okay, now here. Sorry, let me sketch first lah. To this point. All right. So for the orange color, it should be here. Okay, for the next half cycle, we apply the current pulse to turn on T3 and T4 or S3 and S4. So mean your current pulse will be at this point. So this is for S3 and S4. Okay, so then you can sketch for the output voltage here because during angle here from 45 to what's the value of this angle? Maybe this angle will be what? So this is 45. So this angle will be what? Someone can give the answer. This point. So this is pi, right? Pi. So mean here will be 180 degrees plus 45. You right? Pi plus alpha and pi plus alpha in radian. So it means when you inject the current pulse for S3 and S4, so then S3 and S4 will be conducted. So I mean this is the output voltage. So suddenly change to positive value here. So then it will same as the inversion of Vs until to this point. So during this process, and during this angle range, S3 and S4 will be conducted. Okay, will be conducted. Then you apply the current pulse for the next cycle here. So this current pulse to be injected to the gate terminal of S1 and S2. Here will be for current pulse for S3 and S4. Okay, so then you can sketch the output voltage here. Suddenly change to the positive value at this point. Then in this case, your output will be same as Vs. Vs. Then you inject the current pulse for S3 and S4. So then your output suddenly change to positive, but this case your output voltage is equal to minus Vs, an inversion of the source voltage. Okay. So maybe I can here just to get the clear picture. So during this interval, S3 and S4 will be conducted. So this case, your VO, maybe I write here, your VO equal to what? Minus Vs. But now you inject the current pulse here at this point, S2 for S1 and S2. So this case, your S1 and S2 will be conducted at this interval. So where your VO will be what? Your VO will be same as the source voltage, Vs. Okay, so please analyze how to get the output voltage. Because this one you have already learned last year. Subject what? Power electronics subject. And no need to discuss in detail. Okay, clear? Here, maybe we can extend to sketch this waveform here. So you get this point. Okay. So where the green color of the waveform is the output voltage. The instantaneous value of the output voltage waveform. Clear? Maybe I can extend this point in order to get clear understanding how to generate the current pulse. So where this gap, this alpha, right? Here will be what? Here will be pi. So then this point, same gap here, is alpha. Sorry, maybe I need to alpha. So mean this point will be pi plus alpha. Please understand how to design the current pulse. So remember, you have another part of midterm question number 2. Question number 2, maybe next week. So answer in group assignment. So let's say I give the question during class. So you must submit the solution or email to me before 12 at night, at midnight. Okay, one day. And next week. You can answer by group. So in the question, it have 2 parts. First, you need to do the calculation part, and then the verification part through the simulation. Very simple, and no need to worry. So one of the question, you need to know how to design the current pulse. Okay. So, okay. Okay, then so this is for the rectifier operation. Now is 11:46. Okay. Okay, the converter can operate as inverter operation where you set the alpha, the angle between 90 to 180 degrees. Nampak? So this, your output will be negative here. Here will be positive. Okay, let's say in order to scale the waveform, we need to provide the example here. So where this case, maybe your angle, example, the delay angle is what? The range between 90 and 180. For example, maybe 135 lah. Okay, mean 90 plus 45. Example, for example. Okay, this case, how to scale the waveform? Okay, remember, this is your source voltage, VS. Your VS with the red line color here. Red line. Okay. So this is the red line. So you see, this is the red, is the source voltage. So where the source is the sine function, right? There are the positive swing minus negative swing, positive and negative. Okay. So this is your source voltage. Okay, for the case, alpha is 35 degrees. Okay, so where your current pulse? How to scale the current pulse first? So here is 90 degrees, right? So here will be 180. So mean your delay angle 135 will be at this point, somewhere around this point, right? So this is your alpha. Clear? Alpha. So this point is your alpha. Okay. Let me sketch first before I explain. Mean so mean this point here, here, Okay. Okay, class, for the first half cycle, put me here blue color and blue color. First half cycle means from 0 to pi. From 0 to pi. So you need to inject the current pulse to turn on S1 and S2. And S1 and S2. S1 and S2. S1 and S2. Same current pulse to be injected to the gate terminal. S1 and S2. So means here, the current pulse is here, right? This is your alpha. So where your alpha is 135 degrees. So mean you can sketch the current pulse. So this current pulse to turn on S1 and S2. Clear? So once you inject the current pulse to the gate terminal S1 and S2, so these two SCRs are conducted and will be conducted. So in this case, your output voltage suddenly goes to here. So where your output voltage same as VS. Same as VS. Nampak? Dia sama dengan VS ni. The dotted red color is source voltage VS. So VO equal to VS. Until to here. So during this process, during this region, macam mana nak buat ni? During this region, S1 and S2 are conducted and will be conducted. So where your VO equal to VS, the source voltage. Okay, source voltage. Remember the source voltage, the dotted red color of the waveform. Okay. Okay, now for the next half cycle, you need to inject the current pulse to turn on S3 and S4. S3 and S4. Here. S3 and S4. For the next half cycle. So mean from apa? Next half cycle lah, from pi to pi. To mean here, you design the current pulse at this point. Nampak? Same current pulse to be injected to the gate terminal of S3 and S4. Okay. So what is this angle value? Ni. Berapa ni? So it should, the value here must be pi plus alpha. Is it right? Because your pi will be here, right? This is your pi. Ni pi kan? You try to extend this line. So then you get, here will be pi. Right? Then the gap between these two lines will be alpha. Then you inject the current pulse at pi plus alpha, which is what? Pi plus alpha will be 180 plus 135. 315. Okay, 315 degrees. So once you inject the current pulse to gate terminal of S3 and S4, these two SCRs will be conducted. So mean your output voltage suddenly change to here. Because of what? Okay, I try to extend this line first. So mean during this angle, now your S3 and S4 will be conducted, right? Where your output voltage will be what? Minus VS. Minus VS. The inversion of the source voltage. So that's why I sketch this waveform ni, the grey color waveform. And so the grey color waveform is actually the inversion of VS. What? Inversion of VS, minus VS. So it means during this range, your output will be minus VS. Minus VS. What ni? The grey waveform. the dashed line grey waveform. Clear? Okay. So then you can sketch lah, because this waveform will be repeated. So mean here for the next cycle, the current path to be injected for S1 and S2. Here will be current path for S3 and S4. Okay, S3 and S4. So when the current pass, when the S1 and S2 are turned on, your output voltage equal to the source, the dotted line waveform. Remember, the dotted line waveform is the Vs. But when the S3 and S4 conducted, so now your VO will be equal to minus Vs, the gray color waveform here, the gray color. So remember, the gray color here is the inversion of the source. So mean here is the output voltage when the S3 and S4 are turned on. Okay, so this is the way you sketch the output current, the output voltage. Sorry, the output voltage. Okay. So the green color here is your output voltage waveform. Okay, class. Maybe you can analyze and get a better understanding how to sketch through the simulation. After that, we can look at the simulation. Okay. So from the graph, from the output voltage waveform, so actually for the case number 1 here, and case number 1, so we know that to calculate the DC component of the output voltage, so you must calculate the net area. So this case you have net area. You divide by period. So if you look at for the first case, when the converter operates as the rectifier, so you can see it has two areas, positive and negative area, right? So where the positive is here, the positive area, right? And another one is negative. Negative what color? Orange. Which area will be larger? Positive area will be larger than negative area, right? So that's why for the case number 1, when you set your alpha is 45, the positive area is larger than negative area. So mean your net area will be positive. Correct? Net area is area positive area, you subtract with the area negative, then you divide by T. For the first case, the positive area will be larger than negative. So that's why your net area will be positive. So then your output voltage is positive. Okay? Clear? Okay, for the case number 2, you operate the converter as the inverter. Converter as the inverter. You set your alpha is 135. So from here, you can have the negative area now is larger, right? This is your negative area. But the positive area now is small, right? Become smaller. In order to calculate the DC output component of the output, so you need to get the net area. So the net area is the different positive area and negative area. The positive area now is smaller than negative area. So then your net area will be negative, right? Net area. So when your net area is negative, then you get the output voltage value is negative. Okay? Okay? Boleh kan? Lepas ni kita rehat sekejap. Pukul 12. Siapa ajar power electronics? Dia ada cerita tak benda ni? Ada kan? Saya detail with my style of apa teaching, I'm very technical. I provide more picture because picture give 1,001 meanings. We try analyze from the diagram or picture. Okay, let's take break for 10 minutes before we proceed to do the exercise. 10 minutes, Okay, ready. Itu. Boleh ya. Teruk ah. Okay, class. Okay. 12:10. Okay, before we proceed to discuss the exercise, let's take a look the simulation first. Okay, so we have discussed that when you set the angle between angle 90 to 180, so your converter operate as inverter. So for example, here I set 135 and 135 degrees. Okay, you can see and the negative area now is larger than the positive. Is it right? The negative will be larger than positive. So here is the 0 and 0 1. So this is the time axis. So where you can see the area below the time axis, which is the negative value, is now larger than the positive. The positive here, very small portion, a very small area compared to the negative. So if you say you set your angle is 45, so now you can see the positive area will be larger, right? Because the output voltage above the time axis now is larger, and the area is larger compared to the negative, or the area below the time axis. Okay, so how about when you set the angle now is 90? Okay, remember for 45 degrees, your converter operates as a rectifier. And 90 degrees, so where you can your output voltage component will be what? 0, because your positive and negative area same area value. Positive and negative give the same values. So let's say we try to verify. You can see the area of the output voltage above and below than time axis is same. You can see this is the time axis. So where the positive area here will be same as the negative area. Okay, for the case of alpha is 90 degrees. Okay. Okay, now we go to discuss for the simulation. The simulation exercise, for the exercise. Okay, for the exercise number 3. Okay, so please read the question. DC voltage in figure, the below figure, represent the voltage generated by an array of solar cells has a value of 160 volt. Okay, so remember for the inverter operation, so you must set the polarities like this. The positive at the bottom, the negative must be at the top. So where the DC voltage here is, the DC voltage here is 160. Yeah, positive 160 volt. Okay, so the solar cell are capable producing 5 kilowatt. So mean the power will be delivered by the DC source 5 kilowatt. The AC source is 230 volt in RMS. Your R is 0.86 ohm. Firstly, you need to consider the L is very large enough so that you can ignore the ripple first. So then in part A, for the first part of question, you need to determine the delay angles so that 5 kilowatt can be supplied by the solar cell. Then in the second part, you need to calculate the power transferred to the AC system and the losses. Okay, so here is the solution. So firstly, before you calculate the delay angle, of course, you need to determine the output voltage first. Before that, you need to calculate the output current. So initially, you need to calculate the output current, where the output current you can calculate based on the information of the power. So we know the output current is VDC, you divide by. So remember your PDC, power delivered by the DC source, is multiplication between VDC and IO. So from here, you can calculate IO, the output current. So where PDC is 5 kilowatt, you divide by DC source. DC voltage is 160 volt. Okay. So then here is the output current, 31.25 ampere. Okay. So based on the output current, now you can calculate the average output voltage. So make sure you write in capital letter because this is the DC component or the average component. So how to calculate the output voltage? Firstly, you need to obtain the equation of the output voltage from the circuit. The concept. So remember your output voltage, the direction is from minus to positive. So you can have the voltage across the resistor, which is VR, right? So R is the passive element. So mean the direction must be from minus to positive. So then you have the VDC. We define the VDC direction as like this one, from minus to positive. So you apply the Kirchhoff voltage law. So from here, you can obtain the output voltage equation as VO. Or maybe you apply the KVL first, Kirchhoff voltage law. So you get all the drop voltage for each element. So you have the VO minus VR positive, VDC, then you equate to 0. You get all the total summation of the drop voltage for each element equate to 0. Okay. So from here, you can obtain the output voltage equation as VR minus VDC or IOR minus VDC, right? So then here VO is IOR minus VDC. So IO is 31.25. R is what? What is the value of R? 0.86. 08 minus BDC apa? 160 160. So then finally you can calculate VOS minus 133.1 volt. For inverter operation, the output voltage must be in negative value. Negative value. Okay. Okay, then from the output voltage, you can calculate the alpha, the desired firing angle or delay angle. So we know that VO1, your VO is equal to what? We know that VO is what tadi? 2 Vm pi. 2 Vm per pi cos alpha. So you rearrange this equation to solve for alpha. So where your alpha is cos 2 Vm. Or cos VO is minus 133.1 pi 2 Vm. What is the Vm? Vm is the peak amplitude of the source voltage. So Vm based on the question given, the AC source given in RMS 230 and 230 volt RMS. So mean you need to multiply by Z2 in order to calculate Vm. So here multiply by Z2 230 volt in RMS. So then you can get the alpha as 130 degrees. Okay, double check. Because your converter operate in inverting mode, so your alpha must be larger than 90 degrees. I mean your angle must be in range between 90 to 180 degrees. Okay. So the angle 130. Okay. Then apa? You get the alpha because in part 1, okay, part 1 solve lah. So the part 1 solve because this question in this part you need to calculate the alpha. Okay, then the second part, you need to calculate the power transferred to the AC system, PAC, and the losses, the power losses or power absorbed by the resistor. Okay, so here, PAC, so you must write the equation first, which is minus VO, you multiply by IO. Okay, maksudnya power absorbed by the bridge, and PAC is the power absorbed by the bridge. So mean here, so you have the VO across plus to minus and the bridge input and plus to minus and the current. So where your VO is minus, put the bracket here. So where the VO value is minus 133.1 multiplied by IO 31.25. So remember, your output current must always be positive. And for rectifying mode and inverting mode. Okay, current always positive, output current. Okay, then here you get what? 4159.375 watt. Okay, power absorbed by the resistor. So RMS value squared multiplied by the resistance value, or you can equate the RMS current as IO. IO. So here you get what? 31.25 multiplied by 0.86. $625 watt. Okay. Okay, for the converter operate as the inverter operation. So mean your power transferred from the DC source to the AC. So maybe you can double check your calculation here, the above calculation. So we know that your PDC must be the summation of PR plus PAC. PR is the losses, PR the power absorbed by the bridge. So when you check, you get 5K. And okay, just to check your answer. Okay, very straightforward for this chapter. Simple. Okay, now we move to exercise 4. Exercise 4. So actually, exercise 4 is extension from the exercise 3. Okay, so you apply the information given in the question exercise 3 to answer for exercise number 4. But this case, you need to determine the value of L, the value of inductance, in order to limit the peak-to-peak current ripple to 2 ampere. In part 1, in exercise number 3, exercise 3, we ignore the effect of L. All analysis in this, you apply DC analysis. But in exercise number 4, this time you need to consider the effect of L. Because you need to limit the current ripple, the output current ripple to 2 ampere. Okay, so in order to answer this question, first, in order to simplify the analysis, so you must apply the assumption where the peak-to-peak current variations is mainly affected or influenced by the first AC term. So what is the first AC term for the single phase rectifier? Your N is what? N equal to 1, 3, 4, 5. N is 2. Because if you look at the waveform, the waveform, where's the waveform? For the one cycle of the source voltage, so actually you can have 2 cycles of the output voltage and output current. So that's why the first AC term is 2. I2. So means here, the first AC term is when the order of harmonic is N equal to 2. Which means I2 lah, I2. I2 Okay, so in order to understand what it means, the assumption, so maybe I can provide this illustration. So you can see here is the output voltage, the green color, and the output current. So the dark blue color is the average component of the output current, which is constant at 31.25 ampere. Ini you dah calculate in part 1 kan, exercise 3. Okay, the design requirement, you require the design, the circuit require the current ripple to be limit at 2 ampere. Ni. Between the maximum and minimum. Okay, so actually your output current you can write in Fourier series. So where the current, the instantaneous of the output current is the summation between the DC component. So this is the DC component plus the total summation of current harmonics. Right? Current harmonics. Ni kalau you nak write the equation or in Fourier series. So you already get the IO is 31.25. And in order to simplify the analysis, so we can ignore the higher frequency component, which is N4, N6, and the rest. So means, in other words, the current ripple is only affected by the first term, which is I2. So there I4, I6, I8. Since the value are too small, then we can neglect. So the only term that influence or affect the current ripple is I2. Understand? I2. So that's why in this case, we ignore all the current harmonics, I4, I6, and the rest, and until infinity. So you just consider only the first term, which is I2. Sorry, actually this equation n is equal to 2, 4, you can have 6, 8, blah, 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 until infinity. So in order to simplify the analysis, we just consider the first term, which is I2. I4, I6, I8, ignore, because the value, the current amplitude are too small. Okay. So mean I2, I2. So based on this equation, kalau you try to illustrate, so actually to get the IO, and the blue color is IO, and is the summation between the average component IO and I2. IO and I2. IO is the DC, I2 is the AC component. And they varies around 0 ampere and 0 ampere. So mean the current ripple, based on this illustration, we can say that the current ripple is same as the current ripple of the I2. Nampak? Ni, I2 ni. The current ripple for I2 same as the output current ripple. Okay. Okay, the design requirement kita, the change of IO is, the required IO is 2 ampere. So based on this waveform, so actually you can have the peak of I2 current, which is what? I2 is peak to peak, minimum to maximum. Minimum to maximum. But for the amplitude I2, so the value will be the change of IO divided by 2. Betul? So you get 1 ampere. Ataupun kat sini, saya zoom. So I2 ni you define is as what? The peak of sine waveform ni. So this is I2. Betul? Peak to peak is the current ripple. Current ripple size, peak to peak. Daripada peak to peak, maximum to minimum, 2 ampere. But now for I2 is the peak value, mean from 0 to the maximum, which is 1 ampere. Because peak to peak is 2 ampere. Peak value is 1. You get it? Boleh? Okay, then. So then. Okay. So because the design requirement, the current ripple is 2 ampere. So mean from here you can calculate I2. So where your I2 is the current ripple divided by 2. So your the required current ripple is 2 ampere divided by 2, you get 1 ampere. Is it clear? Boleh? Senang ini. Okay, then we know that the required load impedance Z2 is equal to V2 per I2. So actually this equation based on the general equation, which is Zn, the ratio between Vn and In. So because we consider for the first AC term, your N will be 2. Okay, firstly you need to estimate the V2 first, the voltage component for N2. So where you can estimate the V2 from the graph below. Ini senang kan? So your alpha, what the alpha? Your alpha value is what? Alpha is 130 degrees kan? You have calculated in exercise 3. Exercise 3. So where? Mana? Alpha 130. Sini betul? 4, 5, 6. So here. Then. Okay, so here is your alpha, your calculated alpha, which is 130 degrees. So then this point will be Vn, which is V2, right? V2 divided by Vn. So based on this graph, you can obtain the value of this ratio is what? 0. What? 0.7. 0.7. Okay, because we just concentrate for the first AC term, which is N equal to 2. Okay. So then from here, V2 per Vm, you can calculate V2 as 0.7 multiplied by Vm. So where Vm is what? 0.7. So Vm is the peak value. So you need to multiply by Z2, the RMS value, 230. So then here you get 227.69 volt. Okay, then you can apply this equation to calculate the required impedance. Okay, we go to the next page. So therefore, Z2, we know that Z2 is V2 divided by I2. So your V2 is 227.69, where your I2 is the peak, which is 1. Then you get 227.69 ohm. Okay, then you need to apply the assumption in order to simplify the analysis or the calculation. So the resistor given value is 0.86, 0.8 ohm, which is too small compared to the total impedance, which is 227.69 ohm. Yeah. So we know that the impedance you can calculate as square root of R squared and omega L squared. So because we consider the R is too small, then you can neglect the term of R. So then your equation now can be reduced to what? Can reduce to what? N omega L, right? Because you neglect the effect of R. The R value is too small compared to the total impedance, 227. So then from here, you can solve for L. So you just rearrange the above equation. So here is Z2. So maybe I can write here as N first. N omega L. So where Z2, Z2, 227. So N is what? 2, N is 2. Omega is 2 pi F. 2 pi. Frequency given, what is the frequency value? So maybe we can assume the frequency 50 Hertz. 50 Hertz. Then finally, you can solve for L, which is 0.362 Henry. Okay. You determine the value, the appropriate value of L in order to limit the current ripple. Okay. So remember, the effect of inductance, inductor, actually it can minimize the current ripple. In order to minimize the voltage, so you need to design for value of capacitor C. Okay, finish. Okay. Before we end our class, so let me demonstrate the simulation in order to verify the calculation. So this is exercise 1, exercise 2, exercise 3. Need to close first. Stop. Sorry. No. Then open which one? Single phase. Ini. Slide 40. Okay, this is a simulation model for exercise 3. Let me resize further window. Mana? Okay. Okay, for this simulation model, I generate the current pulse using pulse generator. Pulse generator. For your midterm question next week, you need to know how to design the current pulse using the current pulse generator. So I don't want to discuss this one. So you think how to design based on the illustration that we have discussed in class just now. So please think how to design the current pulse using the pulse generator here. Soalan bocor ni. Okay. Okay, so believe me, so you just trust to me. The current pulse we set here is what the value just now we calculate is what? 130 degrees. 130 degrees. So where is the current pulse? Here, 130 degrees. So mean we try to operate the converter as the inverter operation. Okay, so this is the simulation. Your bridge. So make sure your polarity of the DC source in the right way, in the right polarity, plus at the bottom, minus at the top. Your value of RL. Remember your R is 0.86. Your design L and your required L is 0.362. 362 kan? 362 ni. 362. Okay. Here 362. 362. Okay, then your DC voltage is 160, betul 160 from the question, 160 volt. Then your source in RMS is 230. So you need to multiply by set 2 because this parameter box require in amplitude. Okay. Okay. Okay, then apa kita try to simulate. So this run the simulation. So in order to make the simulation run faster, it is recommended to close this scope window ni. You tengok, you boleh compare dia punya progress. So now it's 8%, 9%, 10%. Okay, we wait until 100%. Okay, tomorrow class. So we start at 8:15. Okay, 8:15. Here, BK1. So maybe tomorrow will be the last. And we discuss on 3-phase rectifier, control 3-phase. Maybe we can have a revision, guys. Okay. Now is week number what? Week 13. We have 15 week. So now this week is week 14, 15. 12. 12. Week 12. So we have 2 weeks. 2 or 3? 2. Okay. Tak ada, no class. Okay. From the scope here, sorry, the display block here. This is the display block. So you can see the result for the DC component of the output voltage and output current. So you can see here, by comparing between these two results, the RMS value and the average are same. RMS and output current similar lah, is similar. Okay, so ni mana tadi? Your calculation. Where's your calculation? Your VO is minus 1331. Betul minus 1331. Sama, exactly same. The output current 31.25, here 31.24. Almost similar. Okay, so complete running. Okay, then we can see the result simulation by double clicking the scope here. Okay, so the top graph is the first graph is the waveform of the source and the output. The source yellow color, the output is the blue color. So where your VO is negative because the negative area is larger than the positive area. So that's why you get the negative output voltage, minus 133.1 volt. Okay, second graph is the output waveform of output current waveform and the source current. Your source current is here almost to the square wave shape because of the inductance, inductor. So the yellow color is the output current, always positive, because this is the reactive Okay, this is the current path. The third graph is the current path for current passes for T1, T2, and T3 and T4. T1, T2 yellow color, the blue color for current path for T3 and T4, and thyristor 3 and thyristor 4. Okay. Okay, then in order to verify your design, the inductor value design, so you can check the current ripple because the question require the current ripple to be limited at 2 ampere, the current ripple 2 ampere. You zoom you magnify, further magnifying the result, then you can calculate the difference between the maximum and minimum. So maybe the maximum almost 32 ampere, the minimum 30. So then the difference is almost 2 ampere. Okay, dia terlebih sikit lah. Dia ada error sikit, but the result is acceptable because when we consider in percentage, the percentage is still less than 5%. So the result is acceptable. Okay, that's it. Finish for today. Okay, for tomorrow we discuss on the 3-phase. Okay, any question? No question. Everything is okay. Okay, so this evening, so which group want to do the experiment? You can come, maybe 2:30. So don't worry, we have much time, so maybe you can proceed. Those group that we don't the slot time, you can go for the next week. All right, thank you. Assalamualaikum.